Hello everyone, my name is Mark and welcome to tutorial number 4 of Dagster. So this is the fourth tutorial in a series of maybe 5, we'll see how we go. Anyway, so welcome. So previously, that is in the last 3 tutorials, we covered respectively an introduction to Dagster, what it's all about and the background. We also just went through a process of describing all the elements of Dagster. And we also went through tutorial number 3 where we sort of went through several practical invocations of how to use Dagster. So in this tutorial, we're kind of going to extend that a little bit further. So I'm going to give you an extra example of how to use Dagster that's perhaps a little bit more involved. And I'm also hopefully going to walk you through some of the elements of the actual source code of Dagster so that you can understand how Dagster is, code-wise actually pieced together. Now, in the previous tutorials, we went through 3 case studies. So particularly, we went through a case study of Costas arrays. We went through pentominoes as an example, and we also touched on determinants, I believe. So these are 3 example case studies that were published in AAAI and Pre-Chi respectively. Hopefully, you have links to those kinds of programs. But in this one, we're going to have another tutorial, another case study as well. All right, so what are we going to do? We're going to have a more involved case study, specifically bounded model checking of protocols. And also we're going to have a deep dive into the source code. So, let us begin. Case study. Protocol model checking. Subtitle, splitting by variable fidelity. Alright, so, bounded model checking. So, basically, one of the things that SAT can do, right, is model the control flow of a program. If you've got a program that you've coded in a respective language, then you can download or install or run various model checking programs on it. So, for instance, in the case of C, the language C, if you have a C source file, you can download and use a program called CBMC, C Bounded Model Checker. And if you annotate your C source, what the Bounded Model Checker can do is it can actually reason whether a specific error state that is given by your annotations can or cannot be reached. And what it does is it takes your C program and then it munges all of the details about that and then outputs a SAT file or a SAT program, which it in turn can solve to demonstrate whether a particular error state can be reached. And this is, mighty handy, depending on various things. So let's take an example. So for instance, up here in the top left, we have an example of a very simple program. So we have, an undefined integer x1, which could be anything, and the SAT solver knows it. And then you have a couple of operations on x1, and then you have a condition, and then you've got an annotation, C prover assert, and then error state, I did a boo-boo, which can actually be reached depending on what value x1 is. Anyway, so basically, if you pass it into CBMC like so what it does is it says it converts it to a SAT problem, and then it solves using mini-SAT. It's got 1,810 variables, 9,000 clauses, which is a lot, but for such a simple program. But anyway, it basically computes in 0.006 of a second that it reasons that yes, it can actually indeed reach the error state, which, actually is pretty true. Particularly if x1 is actually 0. It's pretty easy. In any case, so this is just an example run of how to use CBMC. Now, the advantage of using CBMC is basically that if you have a logical process that you can code, that is to render into C code, right, and then you have a question about that process, right, then you can throw it into CBMC and it can reason about it, which is actually pretty flexible because, in principle, you can code many things. Right, so you can do SAT reasoning about any logic that you can code, at least in principle. And anyway, so one of the things that we do in this case is that we're interested in coding up, say, an emulation of a computer protocol, a communication protocol between actors. And so particularly in this case, the error state is where the protocol is broken. So, in this case, we have like actors that are good actors and then bad actors, and then, the error state that, the CBMC reasons to is if it is possible for the bad actors to get the information that the good actors are trying to hide, for instance. So, for instance, this is sort of an example of a pseudocode. So we have the sum total of communicated data x1, and then what happens is each actor in turn communicates. Actor 1 communicates, Actor 2 communicates, Actor 3 communicates, using all of the data that has already been communicated by the previous actors and so forth. And then, like if Act 3, let's say who is our bad actor, has the secret key, then we cprove or assert an error state, and we throw it into CVMC to see if it can be reasoned about. Now, one of the things that is true about encoding protocols in C, and then perhaps subsequently interpreting them using CVMC, is that we can describe the protocols using different elements. So, for instance, like, with different packets or different hashes or IDs or headers, etc. And particularly between these different modeling of the same protocol, like a hack may or may not be present. So, particularly one of the easiest straightforward is that because CVMC models all of the bit values of the variables that it uses. So a hack that may be present at, say, 32-bit or 64-bit variables might also be present with 8-bit variables, and then subsequently be an easier problem. So one of the things we can do, is because CVMC programs in SAT can become rather large, one of the things we can do is we can solve the SAT problem for a hack at a lower level of variable resolution, and then subsequently attempt to verify that same approach and that same hack can be manifest at a higher level of variable resolution, particularly via the propagation of abstraction invariant variables, that is, flags that control, say, the execution flow or the particular approach that's taken by the actors in the program. That is, that these variables propagate between different abstractions or modeling of the same protocol. So, the simple idea being that if you have a lower fidelity model, you can solve that perhaps in SAT using a little, more expediently, then propagate those AI abstraction invariant variable values to the higher fidelity model to verify that the attack also works consequently there. So, in our research, we've kind of experimented with different protocols. One of them comes from this particular paper here. Lightweight security protocol for ultra-low power ASIC implementation of wireless implantable medical devices. You can see this in the full publication of the paper, and also the approach is also more detailed in the paper that we've been accepted into PRECI, that is the Pacific Rim International Conference on Artificial Intelligence as of this year, 2022. You should also have access to that. But yes, so there's also, in the repository, there's another example of a protocol as well. So, but anyway, let's just focus on this one. So what we're going to do is we're going to walk through this thing, and I'm going to show you exactly how we can solve this using Dagster. Okay, so the protocol consists of communication between a base station and a medical device, and with the presence of an attacker. And what we do is we basically show that this particular protocol that is outlined in that paper is subject to a denial attack, a denial of service, whereby the attacker can intervene and then subsequently destroy any possible communication between these two elements. So, the process is relatively simple. So it's a protocol designed for low-powered devices. So it's a relatively simple protocol, and we're going to describe it. So the base station has a 64-bit message that it wants to send to the implanted medical device, the IMD. The base station also has a 32-bit serial number and a 32-bit message counter. So serial number S, message counter B. So what happens is for the base station to communicate with the medical device, what it does is it adds one to its own message counter, right? And then what it does is it produces a message like so, which is, so what it does is it takes the message that it wants to send X, and then it takes a concatenation of the serial number and its message counter, right? So that's the 64-bit message, and then the 64-bit concatenation of the serial number and the message counter. And then what it does is it interleaves those two on a bitwise basis to produce a 128-bit value. And then consequently it splits that into two even parts, M1 and M2. The base station then subsequently sends the message that is M1 encrypted with a key K, that is conjoined or concatenated with M2 encrypted with a key K to the embedded medical device. So what happens is the embedded medical device, or implanted medical device, receives M1 encrypted with K conjoined with M2 encrypted with K, and then decrypts with K, the shared key, and then joins and deinterleaves to find the original sent X, S, and B. That is the message, the serial number, and the counter. The IMD receives this message. It checks for a compatible serial number, right, because it doesn't want to receive from something that doesn't have the correct serial number, and then drops the message if S is not recognized. And then it checks the message counter B against its own internal message counter A. Now, if the B is greater than A, right, then it accepts the message and sets A to be consequently equal to B, or otherwise it drops the message, right? So this is the protocol that is outlined in that paper. And we will show how this protocol is subject to an attack. So, question to the audience, how is this protocol subject to a denial of service attack? All right? TikTok. I mean, I could pause here, but I'm not going to because that'd be just terrifying. Anyway, so the answer is, well, the attacker intercepts the communication and then reinserts M2 encrypted with K conjoined with M2 encrypted with K. And I'll show you how this works. So the idea being that the base produces M1 and M2, which is the splitting of the interleaving of X with S conjoined B, and then produces M1 encrypted with K and then M2 encrypted with K and then sends that. So what happens is a hypothetical attacker intercepts this message, that is M1 encrypted with K conjoined with M2 encrypted with K, and then transmits M2 encrypted with K conjoined with M2 encrypted with K to the implanted medical device. Now, what's important here is that the attacker can do this regardless of whether it knows what K is or regardless of any of the message contents. It just needs to duplicate one part. So consequently, what happens is the implanted medical device receives the M2 encrypted with K conjoined with M2 encrypted with K, and then decrypts each part with K, and then joins and deinterleaves to find something different. So what it finds, through the logic, it finds instead of X, which was the original sent message, it receives a garbling of that. So it receives some completely errant message, Y. It receives a correct serial number, S. But then what happens is it receives a message counter that is not B, but is equal to S, right, via this process, right? So what happens is it decrypts, joins, deinterleaves, and then interprets the message counter being sent as being equal to the serial number. Now, in all likelihood, the serial number S is a 32-bit value that is, in all likelihood, larger than the message counter, and then consequently sets its own internal message counter A to be equal to S, right? And what that does, because now the implanted medical device has a message counter that is huge, right, because it's equal to the serial number, and then consequently it will cease to accept any messages from the base station, which will be sending with the legitimate message counter B, which would probably be much smaller. So this effectively bricks the implanted medical device just because of the presence of an attacker. So this is an obvious vulnerability to this very simple protocol, and one of the things we can do is we can more or less model this process in C and then turn that into a SAT problem and then solve that SAT problem using Dagster. Right, so we do this something like this, right? So we have the full actual code that is the modeling of this is found at that GitHub link down below, which was coded by Thomas Willingham in his summer project. And so what happens is this is kind of a summary of the main components of the code. So we have communicated data x1, which is the sum total of everything that's communicated, and then we have a series of Boolean values that more or less dictates who goes in what order. So for instance, like if IMD go 1, that is the implanted medical device is the first one to communicate, then x1, the communicated data dot append, and then whatever the IMD does to the sum total of communicated data so far. So x1 dot append, IMD dot receive x1. Now obviously the embedded medical device won't meaningfully do anything if it goes first because it's waiting on messages from the base station. But if the base station go 1 Boolean flag, which is unspecified, is true, then x1.append base station communicate x1. So the base station gets the opportunity to append to what's communicated, and then iteratively
each of these turns happens based upon the Boolean values of who gets to go when. And if at any point it is the implanted medical device's turn to go and do processing, and it is the case that the message counter that is extracted by the IMD is less than its own internal message counter, right? That is that the attacker must have intervened to put the messages between the base station and the implanted medical devices effectively either out of order or violated it completely. Then we go to bad error, bad ending, whereby there's a cprove assert flag that the protocol is broken, right? And then we throw this into CBMC, and then CBMC will be able to assert that there is indeed a correct way for this protocol to be broken. So anyway, the full source code is in the GitHub, but the basic idea is pretty straightforward. So we encode it in C, and then we encode it in C with different variable fidelities, whereby, previously the base station has a 64-bit message X and a 32-bit serial number and message counter, but the same attack could obviously be true and hold with 32-bit messages or 16-bit messages and 8-bit serial numbers, right? It's pretty straightforwardly obvious that this kind of attack is not specifically sensitive to the bit resolution of the variables. And so in the GitHub repository, there's actually different encodings of the same attack using different variables, different variable sizes. And the idea being, that if we're able to prove that the attack works at a smaller variable size, and then we can propagate that to a larger variable size to verify that the attack holds for the larger variable size. So as I say here, the attack is valid irrespective of the encryption algorithm, the key K, or the size of the variables A, B, S, and X, and it is only sensitive to the abstraction invariant control variables that instruct the attacker to send M2 encrypted with K, M2 encrypted with K. Right, that's the most important variables. They're abstraction invariant. And so what we do, we prove that the attack works at the lower fidelity model, propagate the abstraction invariant variables as constraints to the higher fidelity model, and then solve to prove that the attack works at the higher fidelity model.
Now, let me show you how to do this. So I will bring up my console and terminal window. So we go cd desktop Dagster. I need to make... Actually, I haven't compiled this one. I need to do that. Give it 1 second. Alrighty. Inside of the benchmarks, now I'll blow this up a little bit. Hope you can see that. There's BMC, bounded model checking. Alright, now what we want to do is we want to go to, I think it's 2? There's 1. Yes. Anyway, so in BM//1, there's a generate.sh, which will do all of this processing for you. So the idea is that inside of this directory, so we've actually got a coding of the embedded medical device. So emd8.c is the C program that is exactly this protocol encoded with 8-bit variables. So the serial number is 8, the message counter is 8 bits. And so this is, I'm not going to go into the details here, but you, in your spare time, can go for it. And then the idea is that we go, so like cbmc emd8.c, and it will prove that there is a hack. We just do that. And then if we want, we go dash, I think it's dash dimex. There you go. And what it will do is it'll output the CNF file corresponding to what is to its solving process with comments annotating what the variable values are, which is very useful. Inside of this, there's a Python file cbmc joiner, cbmc.py, and so this basically reads in the CNF files, pulls out the variable annotations, and then produces a DAG for this process of solving for one variable fidelity and then propagating to a higher variable fidelity. And then all of that is carried out with a generate script, so generate.sh. Oops, sorry, I need to activate my Python virtual environment. So there's some Python libraries that it needs to run. Let's try that again. Here we go. Boom. and it just did a whole bunch of solving. So this particular communication protocol and the actual solving of it's actually pretty quick because it's not actually very complicated. It's more instructive than anything else. But like what we can do is that now inside of this we have a whole bunch of DAGs and CNFs. So let's take a look at one of the DAGs. So cat, let's go something small. R3264 DAG. Yeah, maybe that's let me open that in a text editor with line wrapping. EMD8. 864.dag. There you go. So it's two nodes. Nodes 0 connected to 1, propagating the respective variables, that is the control flow variables, or the abstraction invariant. And then we have non-overlapping clauses for nodes 0 and nodes 1, corresponding to essentially the same CNF, just offset with clause index. And then we're interested in reporting the variable valuations that is specific to the successful hack at the higher resolution. Anyway, and then that all works. So, yes, obviously, so, you're free to experiment with this in your spare time. So this is benchmark/BMC. There's a little bit of a README there, and so on. Cool. All right, let's return to the demonstration. Anyway, so that will give you an example of, just how to run these things. So, in the benchmarks file, you find a whole lot of goodies. And one of the things that we did was we sort of, with each of these runs, so that is solving for 8-bit and then propagating the value to the 64-bit, versus the 16-bit versus 32-bit versus just directly solving the 64-bit. We kind of extracted out because it's a bit difficult because the runtime is so fast, but we extracted out the number of conflicts encountered in the SAT solving process versus the number of assignments and decisions. So this is more or less indicative of the work that's being done, particularly the number of conflicts encountered. So the idea being here that, you can see that across either of them, doing this propagation techniques doesn't necessarily save you decisions, but it does save you, probably about a factor of 5 number assignments. So this is a log plot on the y-axis. And most notably, it saves you pretty much an order of magnitude number of conflicts in the process. So the idea being, there is a factor of 10 less restarts and less conflicts that the CDC conflict-driven clause learning process actually needs to encounter in order to go through this solving process. So the idea being that with this sort of schema, you can potentially solve more complicated processes and demonstrate vulnerabilities by this propagation of variables between different emulations. Anyway, so that's the case example that I wanted to explore this tutorial, and so now we're going to go on to a little bit more of a complicated thing, and that is sort of more or less exploring the source code of Dagster. Okay, so one of the things about Dagster, in part of sort of the handover of this project, is that, invariably there's going to be, a code base, right? And, it's sort of a bit intimidating to just simply be given a code base and then expected to just know it, right? It's can't you just read source code? And it's while it may be true that, with very well, coded source, you could be able to read it, it is potentially a little bit rude and inconsiderate if I just hand over the whole bunch and just say, go. Anyway, so what we're going to do is I'm going to walk through some of the source code, so it's a little bit more hand-holding, just sort of a little bit of a more friendly way, such that, if you want to understand what's going on or modify anything, that you have the information to do such. All right, so the first thing is we're going to go to, so this is the Dagster directory. So, at a high level, we have a README, which is, when it loads, blah, 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 blah. It should have, if you're one for reading text, that's for you. It has a Docker file of instructions to go through the install process. I don't even know what that is. Anyway, we'll figure what that is. This is a Git repository, so it's got a .git. So most notably, it's got the benchmarks folder where it's got a whole bunch of CNF generators for various things. And then we have experiment scripts, that is, scripts that run those experiments in the benchmark together with the Dagster. We have a folder called Originals. So this holds the source of various parts that were actually used to make Dagster. So there's a sort of like a reference. So for instance, here is the original TeenySat 0.22. So the strengthener, for instance, was coded from like a source code that's actually pretty difficult to find on the internet now. So it's minired/glucored, sort of a bit hard to find. So anyway, so this is there's some stuff in the originals folder. There's utilities that we can get to later, but none of this is particularly particularly unique. So for instance, scramble cnf.py just basically reads into CNF and just scrambles the order of the clauses and the indices of the variables. Because sometimes that can make a big difference in the solving time just by total chance. But anyway, so these are utilities. And then we have the Dagster source itself. So what I'm going to do, I'm just going to make clean cd dot. Alright, so we're going to clean it up, get rid of the O files. Anyway, so what we're going to do is we're going to walk through some of these things. So we're going to go back to the slides. Okay, so the first thing is there are a couple of really obvious things to pull out. So, for instance, like license is the GNU license. I mean, don't be afraid of that. It's just the legalese. Right. Makefile. You know what that is, right? Now, the makefile's anyway, so yeah, it's there. And then there's like tests. I wonder what that contains. Like run tests, minimal tests. There are some minimal tests. And oh, look, there's unit tests. Right. Okay. We know what that is, right? Good. All right, so I contain the unit tests. I am the obligatory GNU license. I am a makefile. I instruct compilation. All right, so this is pretty obvious. All right, so there's other ones here as well. So, for instance, like run scripts. Right, so this is just a whole bunch of .sh. Right, and so for instance, this is just an example of an example invocation of Dagster. So there's some that are interesting here. So for instance, like massive run 2 is like a way of running Dagster with the Valgrind massive tool, which is kind of an interesting invocation for debugging purposes. At least I found. But anyway, so those are just example run scripts for you to do. No particularly core interesting stuff there. Now we have the wizard and the viewer. So, I think in the tutorials this should be relatively familiar too. So the wizard and the viewer, just they're really, really daft, Python files that just throw up an interface to just do something auxiliary. So the wizard particularly, so we can go Python wizard, it's just basically the configuration. So it's essentially like a Python, a small Python utility that just formats the Dagster run command for whatever you want input-wise. And then there's the Python viewer, and we've seen this before. So there's nothing particularly new there. It just viewer parses the log files to spit up onto the screen, information about the status of a run. And then we have utils.h, utils.cpp, and utils.h. Utilities.h. So these are just truly miscellaneous functions, right? Like, for instance, this one, like set random number, like, what is it? Random number generator, right there. Compare the ABS of two integers, right? Is a subset, is this sequence of integers a subset of that sequence of integers? These are sort of like really daft utility functions that sort of, show up only if you need them. Wouldn't worry about them too much. Oh, and exceptions.h. They're just subclasses of exception, for a whole bunch of cases. So let's go to exceptions.h. Right, so this is, I am a parsing exception. I extend std exception. I am a consistency exception. I extend std exception. Blah, 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 blah. This is, like, nothing to worry about here. All right, so we've already scratched off a couple of things. All right, let's keep going. Interactive functions.cpp. I am a legacy interface. Do not worry about me. In fact, I probably have half a brain to remove that stuff, but it's in there for good measure at the moment. So that's interactive functions was originally an experimental kind of feature for some research that was going on here, so that other C programs could be compiled with Dagster to actually launch parallel runs rather than calling on Dagster as a command line utility. But I think this interface code is broken anyway, so yeah, half a mind to delete it. So interactive functions, don't worry about that. Another one, arguments.h, arguments.cpp. So I am the class that holds and parses command line arguments. Right, so inside of arguments.h, we have essentially the arguments class. So, every process has an arguments class that holds exactly the same information. So integer mode, right, blah, 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 or like decision integral, novelty number, breadth first search. So these are all of the configurations that get parsed in on the command line, and they get formatted into this class. Right, so, and then inside of the arguments.cpp, you have the specification of all the defaults for these values, and then like the argparse docstring. So this is, formatting for the terminal window, and then just the code to actually parse in the command line arguments into the appropriate variables. For W, input arguments dynamic circle search mode, right? So W specifies that. Anyway, so this is argparse stuff. Yep, no particular worries there. Let's go back to the thing. Arguments.cpp, arguments.h, I am the class that holds and parses command line arguments. Okay, so now we have a couple of other ones here. So we have disordered array, range set, and reversible integer map. So these are simple data structures. So let's take range set, for instance. We can turn to range set.h, kind of a fun one. So this is a very shallow class, data class. So it's a simple vector of pairs of integers identifying that the contained integers of a set. Identified that the container contains integers of a set. So A, B to C, D, E, F to G, G, H, I, etc. Where each pair is the beginning and end of a range. So for instance, like if you want to have a data structure that stores all the integers between, say, 1 and 100, the number 103, and then all the numbers from 200 up to 1,000,000 in a compact way. I mean, you could put all of those numbers into a vector, but that would be memory expensive. So the idea is that you call a range set, right? And the range set is just essentially it's a vector of pairs of integers identifying the beginning and end of an integer range. That's all the range set is. What's another one? So disordered array. So it's essentially just a vector. Let's turn to disordered array. It's a simple indexical vector class in which elements can be added or removed individually. Note that appending appends them to the end of the array while removing reorders the indices. So the idea being that if you have a contiguous memory block that is an array, you can insert elements in order of whatever kind, so type T, this is templated task. So, and then what happens is if you want to remove a particular element at a particular point, what we will do is it will shift the element at the end of the array to overwrite that specific element at the index that you wanted to delete. So basically, it's a really quick class for vector type class for storing an array of elements, except that the delete operation can make the array disordered with respect to the order that you added the elements. That's all the disordered array is. Now, reversible integer map. Let's go with that one. So, an easy lookup list of integers. So the map stores a sequential list of positive integers into a specified number, and the reverse map stores the position of the list that any specific integer occurs on. So this is specifically integers. So if you want to store the integers like 4, 5, and 6, so let's say you just instantiate a reversible integer map, add 4, 5, and 6 respectively. They will be stored at indexes 0, 1, and 2. And then you say, okay, so what variable occurs at index number 2? What index is number 4 at? And, it'll have a quick reverse integer lookup. So the idea is that it stores a forward and reverse mapping for constant time lookup. Right, so, basically if you had a normal vector and you placed a whole bunch of elements into it, and then you wanted to know, what index does number 10 occur at, descriptors, and then it'd have to, linearly sort through it, or, to do a binary partition. But this thing here is just a fast reverse lookup. That's all this is. So it's not very complicated. So you just append, remove, resize, get forward map, get reverse map, reset, and print the respective class methods. Okay, so this is the dumb stuff. So we have disordered array, range set, reversible integer map. These are simple data structures. They're used wherever they are for whatever purposes as you please. So you don't need to worry about them too much. Run tests.sh. I kick off your tests. Yep. There's another one here called MPI global.h. So let's turn to that. So basically, this is just a bunch of tags for MPI communication. So MPI has messages that send with a specific tag in addition to a data payload. So for instance, like if tag is sent, if the integer is sent 2, that is tag for a prefix tag that has some function in the midst of Dagster. So MPI kill tag is number 9. I mean, maybe that's traditional, who knows. And then there's also like these essentially what's the word? Basically, macros for just big MPI aborts, right? So you just call bomb error. Anyway, not too complicated. So these are just flags, really. Let's turn back to the slides. All right, MPI flags. All right, now we're getting into the more substantial stuff. So dag.cpp, dag.h. So throughout this tutorial series, we've kind of talked about and looked at various examples of DAG files. So this here is just simply the class that loads in a DAG file and does some very basic checking that it's, the DAG file makes sense, right? So this is file loading and syntax checking and parsing into a data structure. So let's take a quick look at that. So let's go to dag.h, right? So this here, so we have like the number of nodes in the DAG. The node status. So this is particularly if it's like a terminal node or not. We have the forward connections between pairs of nodes, the literals that are passed between forward connections between literals of between different nodes, the reverse connections, that is the opposite of forward connections, the maximum depth of the DAG, the depth of each node for each node in the DAG, right? So if a node is of depth 2, then it is further down the chain of processing than one of depth 1, etc. And the idea is there's check consistency method, assign depths and status. So for instance, if you just pass in a DAG file, it won't have depth naturally assigned to all of the nodes, and it has to kind of process what the depths of each node are in order to kind of pull out the execution ordering. There's also like other checks in here, so we can turn to the dag.cpp. So this is the body of the function. So this is in the constructor. There's actually a file loading process. So this is print and this is what is it? Scanf and get C and unget C. So this is actual loading of the file, and then you've got a destructor there. And there's a whole bunch of things. So it's like then it's got like it's got a hydrate and a dehydrate, or you could like serialize, deserialize thing. So if you wanted to communicate a DAG over the line, you'd have to convert to a serial form and then hydrate from the serial form. So it's got hydrate dehydrate function, and then it's got these consistency checks. So for instance, one of the things is that in principle you could input a DAG that has like cyclic connections, right? So there's an actual check that makes sure that doesn't happen. Assign depths and status, and then print, for debugging purposes. And that's dag.cpp. So dag.cpp, we load and verify and hold all information about a DAG file. Now, particularly, like none of these this DAG file is designed to be relatively static. There's no modifier methods in the class structure. So this is sort of one of those things where every process loads in the DAG file, and then uses that as a reference in the processing. So it's not too complicated, but it's kind of an important data structure. All right, now this is where the meat gets here. So this is the CNF data structure. So this holds all of the clauses that are relevant to a processing. So this not only just reads in a CNF file, but it also has modifier methods. So like, if you want to add a clause, or you want to remove a clause, or you want to reorder the variables, or you want to know what variables occur next to what others, this is the data structure that has all that. So this is a complicated one. So let's turn to cnf.h. So there's license header. Now there's a couple of simple things here. So, VC variable count, CC clause count, int star clauses, so the two-dimensional array of all of the clauses in the CNF, int star of clause length, so so this is like the length of each of the clauses, and then there's a boolean for dereferenced. So this is basically are these pointers pointing to other data elsewhere, or are these actually created by the CNF class itself, at which point it needs to free them on a destructor. So there's various constructors, file name input, and if you want to file name input loading only specific variables, and then there's destructor, or you can create a CNF from already existing data, dereferenced or not. And the CNF also has like a hydrate, dehydrate, so a serialize, deserialize. So you can convert the CNF class as it is to serial form to communicate over the wire using MPI, and then rehydrate it elsewhere. You can also output the CNF file to a specific file. You can print it. You can load it from a file pointer, or you can load it from a file pointer using only subset of indices, etc., etc. Add clause. You can join two CNFs together. There's also a buffer of, which you can compute. So compute occurrence buffers, compute variable neighborhoods. It's information about, what clauses do specific variables occur in. So that's the occurrence buffer. So, if I wanted to know what clauses variable 4 occurs in, I've got occurrence positive 4, and then it'll be a list of the indices of the clauses in which that variable occurs. And then there's also variable neighborhood. So, it's like, do variables 5 and 6 occur anywhere between, occur together in a clause at all? So those are the neighborhood buffers, which is relevant for the SLS, the novelty routines. They use them. So this is all of the elements of the CNF class. So this is, it's sort of loading CNF with a bit of verification, output, input, some modifiers, and also computing relations, so occurrence buffers and neighborhoods. So that's the CNF. Right, so that's a really, really core data structure there. CNF.h, we hold, access, load, change all information about a CNF, and we are not static. Cool, alrighty. Now, those are the obvious stuff, or at least the obvious and important stuff that holds throughout the Dagster thing. So recall in a previous tutorial we had this schematic here, which showed that there's masters communicating with one of several workers. Those workers communicate with one of several SLS helpers and a strengthen a process optionally. And then the master also has work storage, which I think in the last time we identified was either table storage or BDD storage. So this is the schematic of the parts of Dagster as they interact. And so what we're going to do is we're going to break the rest of the source code files up by what part of this architecture they refer to. So particularly we're going to begin with the relationship between the master and the work storage that master has and has access to. So these are the storage that master refers to. So master needs to keep track of all of the work that has been done and needs to be done, and all the work that has already been done. And so what it does is it does that via two different methods optionally. So it can store all of the work that has been done and needs to be done in its logical form as binary decision diagrams, which is a specific logical form for the formatting of these logical structures. Or it can just directly store them as being arrays in one big just table, right? So there's a solutions interface.h, and that's a virtual class, which it's just got virtual methods that are template. And then the BDD solutions.cpp, table solutions.cpp instantiates that virtual class, which then master can use either way. So let's take a quick look at that. We have solutions interface.h, right? So we just got a bunch of very simple, like 1, 2, 3, 4, 5, 6 virtual methods that this thing must solve. So whoops, wrong virtual class. I'm looking at the wrong thing. Solutions interface.h. There you go. We've got 1, 2, 3 classes and another one which is checkpointing. Right. Anyway, so the idea is that with this class, essentially, this is the interface that master calls upon. So the actual master process calls upon this thing to load and get messages from workers. Master calls upon this solutions interface for the storage of solutions from workers and also to get work for the workers to compute. And particularly, these are message objects. So the message objects is it's an object that is directly used to communicate over the line to the worker processes that either tells the worker processes what to do or is the method of the worker processes sending the solutions back to the master. And so there's these solutions interface class says, input a message from a worker that is a solution of message M. And then there's also like message star, give me a message to give to a worker, right? And then get additional clauses is it's a method call that says give me a set of CNF clauses to append to a worker to tell the worker to not generate any solutions that I have already seen before for this node in the DAG, right? So this is like get me the clauses that prohibit a worker from repeating itself. In addition to that, there's also like dump checkpoint and load checkpoint. So the checkpoints are like essentially just a backup feature within Dagster. So basically you give it a file pointer and you say dump to a checkpoint, and it'll dump everything it has, all its memory, to a checkpoint file, which then it can load checkpoint from that file to rehydrate itself all that information from a backup. Right, and then so we have, now these are rather involved class, so we have BDD solutions, which is the interface that is the embodiment of all of that, which then does all of the logical processing of the work that has been done and should be done in terms of BDDs, particularly drawing upon the power of the CUD library, which is include cud.h. And that's a rather involved class right there, which was coded by Eamon Barrett. Anyway, so there's that, and then the secondary instantiation is the table master, which is which is much more basic. It's just storing all of these things as arrays, which is much smaller. So yeah, this has got essentially the same thing, except much less fancy logical processing. It's just big arrays, and it's just processing with array elements. So that's those are the module that master uses to store the logical work that has been done and should be done to each of the workers. So there's a solutions interface, and then there's two instantiations. Now there's another one that master uses called a master organizer. So what the master process does is it draws upon the work to be done from the solutions interface, specifically messages, and it doesn't just directly give them to the workers. What it does is it invokes this thing called a master organizer, which basically keeps track of what workers are working on what messages already, and how those workers should be allocated to the messages that they should be working upon. So, for instance, it is possible in the Dagster processes to have multiple workers working on the same message. Particularly if there's like only one message being processed, it will just throw all the workers at that message. So there's this association between workers and the messages they're working on, and the master needs to keep track of that, and that's what the master organizer class is. So just to recap, the master draws upon the solutions interface to get logical work as messages that needs to be done. It then uses the organizer to assign those messages to respective workers to keep track of the accounting of that. So let's take a look at master organizer. Masterorganizer.h. So it's got a message buffer, it's got an array of workers keeping track of what message they're assigned to and what message they should be assigned to, whether the worker has been polled, where it's looking for a response, and whether the worker needs to be refreshed to switch to a new different message. So this is it's an accounting trick so that master knows not only just what workers are working on what message, but also keeps a buffer of what messages the workers should switch to, and whether those workers are actually in the process of switching to those things or requesting to be or not. And so there's a process here. So one of the important parts of this master organizer class is add message, remove message, get, and then there's allocate assignments, refresh, debug, and then there's also the checkpointing. So that's important too. So we can turn to this. So master organizer, probably the most important thing here is allocate assignments. So this particular method here is just basically a logic around, it tries to equalize the number of workers that are working on the given number of messages. So, like if there's 10 workers and there's only 5 messages, then ideally you want 2 workers working on each message. This is the logic here. Cool. So that's that. And there's also another one here called a statistics module, which basically just keeps statistics on all of the workers working on all of the messages. So particularly when you pull up the Python viewer, the viewer program, and it talks about, like how long it took to do sat and unsat and how many messages flowed in and out of each node. The statistics module keeps track of that, and master has an instantiation of the statistic module. So let's turn to the statistic module. Whoop. There you go. So it's got vectors of worker start times and solution times, and then worker message status, and then node statistics. That is the statistics for each node. It's got constructor, and then it's got it's not very complicated. It's just a module to keep track of the statistics so that the master loop doesn't have to do that. Alrighty, and I am the master class, master.cpp, master.h. So let's turn to master.cpp, master.h. I think I'm getting tongue-tied now. Where is master? Master.cpp, master.h. So the most important thing to note here is that this is primarily a class that just holds the master loop and some data structure that the master loop has. So, in this here you can see there's a master organizer, there's a statistics module, there's a vector of message that is our solutions to the whole problem, which is important. So basically, as workers report solutions to the terminal nodes, basically these solutions are appended to a vector to keep track. There's some subgraph logic. So particularly if your DAG has multiple distinct graphs between the nodes that are distinct, there's there's a specific enumerations mode that is so you can terminate different subgraphs at different times. So basically, and then there's the master loop has track of a communicator. So this is the MPI interface comms. So this is the MPI communicator that it uses to communicate with all of the worker processes. So all of the worker processes are subscribed to that communicator. And it's also got the solutions interface. That is the story of the logical work, either table or BDDs that we referred to previously. So it's got a constructor, it's got a destructor, and it's got checkpointing. And then it's got the loop, which returns a vector of messages that are solutions to the whole problem. So we can take a loop at the master loop. So this is half of the body of Dagster. So I put some big comments in here. So this is the loop. So it's a bit intimidating at first, but it does actually make sense. So while true is probably a good example of your classic I'm a process, I'm doing my thing. And then it's got a flag, so it's got if checkpoint file equals null, then clear all data, otherwise loading from the checkpoint. Log, master is booting from a checkpoint file. Terminate trigger is the flag that's thrown when master goes into the mode of trying to kill off all the workers because the whole thing is complete. And then it's got some clock, some clock information. So this is for timing. So master needs to keep track of the clock signals to parse into the statistics module to store the statistics as it will. Checkpointing index. This is so what happens is because the master process dumps checkpoints to a file, it needs to keep track of what index of the checkpointing it's doing. So it goes 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5 overwrite. So this is the index that it's outputting the checkpoints to, while true. And then so basically, so this is checkpointing logic. So this is while checkpointing not equal to 0 and while time clock minus T2 equals checkpointing times clock point second. So this is output a checkpoint every X many seconds. That's what we're doing here. And then there's also this, it periodically every 4 seconds apparently. Anyway, what it does is it actually outputs a log message that just dumps information from the statistics module. Blah, blah, blah. Anyway, this is just debugging information. Okay, so now this here is this piece of code 119 to 142. So what that's doing is it's essentially it's consulting with the solutions interface to try and pull as many messages from the solutions interface as there are workers existent. So, for instance, ideally, if you have 10 workers, you want them working on 10 different messages, and so master will try and pull up to 10 different messages from the BDDs or table solutions to try and allocate to its workers. So this is so while not terminate trigger, while it's not in kill them all mode, and while the organizer's message buffer length is less than the world size, that is the number of workers, then it tries to message equals master.output message. It wants to generate a message from a logical message of what work needs to be done from the solutions interface. If message not equal to null, if it's able to do that, then start the time and then add it to the organizer, right? And then the organizer will reallocate that to a worker according to its own logic. If organizer.messageBuffLength equals 0, if it has tried to generate as many messages as there are workers and it has failed to generate, and the buffer of messages of work that the workers are working on is 0, in other words, it has tried to generate messages for the workers, there is no more messages, and all of the workers are idle, then we set the terminate trigger to be true, i.e. now master goes into kill all the workers mode. If the terminate trigger is set to true, then we need to do some logic. There's some logic that the terminate. It's been a while since I looked at this code, but there's some logic for the terminate trigger to be true. Right. This is basically saying if the master has tried to generate work for all of the workers and has succeeded in pulling genuinely no more work from the solutions interface, i.e. the logical work to be done so far as the master is concerned is 0, and if there is no work being done on all of the workers, so all of the workers are idly waiting, and if all of the workers are requesting further work, right, because potentially if one of the workers is tied up, then there's problems. So this is a requisite thing. So it needs to be the case that all of the workers are asking for work for then master to coherently just generate the kill signal for each of them, right? Because the workers need to be ready to receive. So that's what's going on there. If the terminate trigger is set, make sure all the workers are polled before exit. Then basically what it does is it just, if this is true, then hard break out of the while true loop. Right, that's what that is. But anyway, if all of that conditions is not set, then organizer allocate assignments. So this is where the master organizer class collates all of the messages and allocates them to the workers or reallocates them as necessary. So basically, if there's new assignments from the solutions interface, then the organizer will allocate them to a specific worker. And what it'll also do is it'll do balancing, right? So like if if there's 10 workers working on one message and then one working on another, then it will balance them out to be 5 each or whatever. And then what it does is it goes through the process. So this here, lines 147 to 173, is the process of sending out directions and instructions for workers to jump on specific messages. So this is for each worker, if the terminate trigger is not true, because it needs to be false if not, if for each worker is asking for work, that is, it's polling master for an assignment, if it is not currently assigned, if the organizer has set there to be an assignment for that worker, if organizer.workers_i.toBeAssigned is not equal null, then what we need to do is we need to get the additional clauses, that is the clauses that instruct the worker to be working only on new things, set the additional clauses to the message, register the sending of the message with the statistics module, and actually send the message. Create a log that the message has been sent. And then there's a bit of dag nodes given assignment.insert. This is the subgraph logic that I didn't code. Anyway, and then basically what it does is that once it's sent the message off, then it needs to free the message that it just created, because that's now registered with the worker across the wire. And then it needs to register with the organizer that it has sent the work to the actual worker, right? So the organizer needs to know that that message that it wanted to assign to that worker has actually been sent to that worker, and then consequently the worker is actually working on that message. Now, conversely, if it is not the case that the worker to be assigned is not equal to null, then what we do is we send a vacuous like poll for reassignment, which will ping pong back from the worker. So this is like, okay, for some reason we haven't got a work for you to be working on. Just take a break and then poll us back for a reassignment in 500 milliseconds. And then we set poll to be false because we have addressed this worker at least temporarily. All right, so now this is the actual sending of the work to the workers. And then now there's the converse thing, which is receiving of the solutions from the workers. So this is lines 175 to 216, essentially. So now the first thing it does is it says comms.receive message. This is like broadcast receive. It's like, so master saying to any of the workers, like, hey, if you've got stuff to send to me, send it to me now. And then basically there's a big if statement here that primarily splits on the tag of the message that it receives. So this is a blocking receive. So for instance, so one of the obvious tags here if the tag that it receives is MPI tag solution, this is like a worker that is sending the master an actual solution that it has found to the work that has been allocated. Receive tag MPI solution from worker X. Then it needs to register with the stats module. Hang on, got a burp. And then, so basically, then there's a whole bunch of things that it needs to do to register the solution that the worker has passed to it. So one of the things that happens is if this organizer.refresh accept, what happens is if the worker returns a solution from a particular node, what that does is that potentially updates the no goods for every other worker that is working on that node. So if for a node in the DAG, say node 3, if a worker is working on node 3 and returns node 3 a solution, say, 5, 6, 7, whatever, then what happens is that every other worker that is working on that same node needs to be updated as soon as it is possible, not to generate the same solution, right? Because master doesn't want to be dealing with duplicate solutions. So basically, this here is just is a flagging the organizer to say that, hey, for all of those other workers that are working on that same node, they need to be refreshed now with this additional no good from that worker that has just returned a solution from that node. The DAG nodes that are generated solutions, this is the subgraph logic just to say, okay, so that node has a solution that has been reported. If the terminate trigger has not been set and the input, then the input message, if it is a terminal node. Right. So this is so a terminal node of the DAG is like one of the final nodes. So basically, if it is a legitimate solution from a final node of the DAG, then what we need to do is we need to, okay, so, do we break out of the loop because we've found a solution to the whole problem, right? So this is master.input message equals 0 is a flag that says, hey, we're at a terminal node. So basically what it does is it solutions, the solutions vector dot pushback a copy of the message M. It's like, hey, we found a solution to a terminal node. And then basically the next logic is, so there's an enumerate solutions mode 2, which is specific to, it's like terminate for a different subgraph. And then there's some very special logic that goes on here that I didn't code, that I don't try to do with. So you can go into that if you want. It's sort of an experimental thing. Otherwise, enumerate solutions equals 0 or enumerate solutions equals 3. Basically saying, hey, we got a solution, let's throw the terminate trigger and, exit the whole thing because, hey, we found a solution. Otherwise, we continue searching. So this is particularly for enumerate solutions 1. We don't break if we find a solution to a terminal node, so we just solutions.pushback message M and then continue. So that's the logic that basically happens if the master receives the solutions from the worker. Otherwise, so there's two other flags. So the first of which is I don't recognize your tag is an error. That's always possible, but I've never had that happen. The other one is the worker can send the master a tag. So lines 178 to 189 is a tag that says basically, hey master, give me some work to do. That is MPI tag request for assignment. So that gets logged. Basically, if the organizer acknowledges that there's no worker that's currently been done on that one, then if the worker has requested a new assignment entirely to be done, then it is finished with the work that it has already been finished, that has already been assigned. So if organizer.workers.i.assigned is not equal to null, then we register that message has been fully completed with the statistics module. We log this thing. The work has been completed, so the message that was sent to the worker can be deleted, and we need to remove that message not only just for that worker, but also for the other workers that have been working on that message as well, right? Because if you have multiple workers working on the same message and one of them reports the desire for be reassigned because they're completely done with the message, then all of those other workers need to be pulled off that message as well. So that's what's going on there at line 185. And obviously, because it's requesting work, it's polling for a reassignment, so polled is true. Now, there's another one. There's a difference between MPI request for assignment and MPI tag poll for reassignment. And so the idea with the poll for reassignment is the worker is asking the master if it should be reassigned to another node. So particularly because the master organizer does like work balancing between the workers, the worker needs to periodically poll the master for the master to be able to tell it to be reassigned to a different message, right? And that's what's going on there. And essentially, basically, that's the master loop. And then there's a send-exit thing. This is if the terminate trigger is set true. And that's the master loop. And the master also has like a dump checkpoint, load checkpoint, which then basically calls the dump checkpoint, load checkpoint of all of its members. So that's the master loop. It's a pretty big part of Dagster. So I am the master loop class. So I am the master. I have statistics module to keep my stats, and a master organizer to organize my messages between my workers, and a solutions interface, either instantiated as BDD solutions or table solutions, to keep track of the logic and to generate messages for my worker. Okay, so that's all of the information that happens between the master and the worker storage, and the work storage. So now we're going to move on to the worker side of the equation. Okay. Now I move to a bit more of a quieter location with an annoying clicking fan. Anyways, so let's kick off. So previously I just explained the various parts of the master loop and the parts that access that, the parts to which master has access to, specifically the statistics module, the master organizer, and the solutions interface. So those respectively keep the stats, organize the workers to the message, and then holds the logic of what messages contain what work should and could be done to the messages, to the workers to complete the project. Now, let us turn to the worker side of the equation. So this is the other side. So the first loop is the worker loop. So this is exactly the opposite side of the master loop. So let's turn to that. Let's do worker. So the worker.h it's just basically I am a loop. There's the worker loop. And it's got some other stuff here. So, and we will turn to this in turn. So some of this may be recognizable, such as the DAG and the MPI comms interface. So this is the MPI communicator that it uses to communicate with the master process. The worker has as well. Then there's the DAG that is a reference copy of the DAG that it needs to use. And then there's some other stuff here. There's other communicators here that it uses to communicate with the SLS processes that it has as helpers, and also the strengthener. Index of the message that it's working on for logging purposes. And it's got a couple of web. So we'll turn to the loop itself. So worker.cpp, and I'll jump through this. So the worker loop is a little bit more stout and commented like so. So big fat while true is a sure sign of a good loop. So the first thing that the worker does is the worker is so there's sort of the communication between the master and the worker is that the worker is polling the master for messages that master initiates. So the first thing that the worker does is it says comms blocking receive, right? It just says, you know, I am a vacuous entity, give me things to do. And then basically what it does is it keeps, so as part of the receiving from master, it has a tag and a message, so a message object. And then basically it keeps an active copy of the last message that it received, so it deletes the old one if there's a new one. And then it breaks depending on what the tag is. So specifically the most obvious one is if it is the kill tag, which is pretty self-explanatory, it's just exit the loop. The other one is there's a tag new assignment. So what the worker does is it has a CDCL process. So this is typically the TinySat or MiniSat. And if there's a new assignment, that is a genuine master saying to the worker, hey, here's a message, go and do this. So what it needs to do is it actually needs to initialize a CDCL solver from that message, right? And then, you know, log that the message has been received. And then what it needs to do is it needs to go into a process of solving the CDCL process for the message that it received. So this is just so line 84 is just the initialization of the solver. And then it says if message tag equals poll for reassignment or new assignment, so then solve and generate message M2. So this is like find me a solution to the problem that you've just been given. Now this here is so poll for reassignment is the flag that master gives to the worker if the worker is to continue doing the solving that it has already been done. So, you know, periodically the worker will poll master if it needs to be reassigned, and then if master says, no, you don't need to be reassigned, it'll poll the same tag back to the worker, at which point the worker will kick off continuing solve and generate messages. Otherwise, if it's the same new assignment, right, if it's just initialized the solver with a new message, either way, it just says solve and generate message M2. Now, the logic that the worker does depends upon the return flag of this call solve and generate message. So if the return flag is 0, that means the worker has finished generating all the solutions to the problem that it has been given. So, you know, this might happen if the problem is unsat or if it has already generated all of the problems, all of the solutions, at which point it sends master a request for new assignment tag. If the return of the result is flag 2, that's the periodic interrupting that the CDCL is doing to allow the worker to poll master for a possible reassignment if it wants. So if the return of the result is 2, then send the tags to master poll for reassignment. If the return tag is 1, so this is the result that says the CDCL is done so that it's actually generated a coherent solution, but it's not done with the thing yet. So then what it does is then it sends it sends solution tag M2 to master. So this is actually send the solution to master that the worker has done, and then solution count plus plus, and then go through a process, basically reset, because it needs to reset after every solution. It's to sort of like, add the negation of that message back into the SAT solving process to find a new one. Now the other one is the CDCL will report a flag 2 that triggers a request for reassignment every X many decisions, if it has that logic in it. But the other one is there's a request for reassignment that also happens after every modulo of solutions. So that's another option here. So if solution count greater than solution interrupt, then send tag for reassignment, etc., etc., etc. And then if kill tag, and then destructor. So this is the destructor. This is free everything, kill everything, unsubscribe to communicators, pass on kill messages. So this is initialize. So this is with the CNF holder, generate the respective CNF from the message. There's some extra logic here. The idea is that the worker is responsible for the initialization and updating of any of the workers that it has, so specifically the SLS and the strengthener. So what it needs to do is it needs to dehydrate the message, so dehydrate message, and then it needs to send that to any novelties and or strengthener, right? Because it needs to actually pass on any request for work, any instruction to do work from the master to the respective novelties and strengthener process. And there's specific logic here for minisat mode. So minisat has this incrementality mode, where basically it won't completely shut down or completely start up the CDCL process between work, depending on what its mode is. So particularly if incrementality mode is turned on, the respective CDCL process doesn't always need to destruct between all work calls. It can actually stick around and save some of those learnt clauses. And so that's the logic that's going on here. So if minisat mode and if minisat incrementality mode equals 1, then do this. Otherwise, minisat incrementality mode equals 0, then do that. Otherwise, then yes, you should delete, because incrementality mode is turned off. And then what's happened is if minisat mode, then new minisat solver. Otherwise, if incrementality mode, append to CNF. And now if it's not minisat mode, then it's using teenysat mode, at which point it's instantiating the sat solver class, which is a different class, but basically the same instantiation of the CDCL process. And then there's a solve and generate messages, which is just basically calling solver.run for whatever the solver is for that specific instance. So this is like actually kick off the CDCL process. Okay, so that's everything inside of the worker loop. Right, so far we've done the master loop, and then the mirror side of that is the worker loop. And the worker, of course, talks to the various CDCLs and the strengthener. All right, what's next? Okay, so extra stuff. So there's other really important things. So there is the message class itself. So this is the object which the master sends to the workers and the worker responds to the masters with. So this basically is the instruction, do work on that node with this message, with these assignments, and also holding the solutions to that. So let's take a look at message.h. Message.h. So there's a couple of constructors. There's like for debugging purposes, there's a clock start time. This is for statistics. There's dehydrate, and then there's hydrate. There's a set, dump to file, read from file, hydrate, and then output to std out. But so inside of the message things, the primary thing is these 4 top variables here. So there's the vector of integers of assignments. So this is like, work on that node with these constraining assignments that is passed across the arc. So this is the vector of integers of those assignments. Then there's the work, right? So this is to node 5 from node 3, right? There's a to and from, so it's actually a message in a sense. And then there's a CNF instance of additional clauses. So this is the additional clauses is like extra constraints that the master gives to the workers to say work on this node with these messages, and also generate every solutions that I haven't seen before. And that's sort of a bit of a difficult thing to specify, except for a set of clauses, right? So this is like the negation of all of the solutions that have occurred from that node before. So it's like, give me new work from that node with these assignments, please. And so that's what the message is. So the message class itself, it's just, it's relatively simple. There's not a lot going on here. All right, so that's the message class. So it's very, very simple, do this object. And then there's the MPI comms interface.cpp and .h. So this is essentially just a small, it's just a wrapper around some basic MPI calls. So MPI has by default like a blocking send and a blocking receive. So this is just a wrapping around some of those basic blocking calls for the purposes of the master and worker communicating. So this is like allocate a buffer to include in an MPI send call that is appropriately sized, right? And this is like, if you're receiving, then, set up the buffer to read the MPI call into, to receive the thing from, and then return as an appropriate message, right? This is, it's very shallow, but it's just sort of like the handy accessor methods to kind of make MPI more friendly. So both the worker and the master have an instance of this class. And this class has MPI communicator object. So this is the communicator is sort of the pool of objects that can communicate between each other at a given index. So each of them will have a rank in that communicator. And master is rank 0 and workers are rank 1 to whatever. And both the worker and the master have this communicator object of a given size, and they have their own rank in this communicator. And there's a buffer, maximum message length is the size of the buffer, etc., etc. So this is another kind of, helper object. Anyway, so message MPI comms. So what we're doing now is we've gone from talking about the master to talking about the master-worker communication. So there's the worker loop, and then this is the stuff that occurs on the link between the masters and the worker. There's also the CNF holder. So this is so there's the CNF object class itself, which holds information specific to a given CNF. But in the process of solving the Dagster, there's like several CNFs corresponding to each node, right? And then there's the holding of each of the CNFs for each of the nodes in the DAG, and that's what the CNF holder is. So we can turn to the CNF holder. Now, the CNF holder is a bit of a funky class, kind of a bit messy at the moment, but the idea is that you instantiate it with a copy of the DAG objects, optionally the CNF directory, which the CNFs will be split into, the CNF file name that you want those sub-CNFs to be called, and a flag whether you want these CNFs to be loaded and set to from the files. Generate decomposition is a flag that is a method that the master calls, such that if the CNF and DAG is to be split into sub-CNFs in a given subdirectory, that it will do that. There's a necessary pseudo decomposition because what it needs to do is it also needs to pull out the clause number and the maximum variable for each of the sub-CNFs that get generated. Then there's a general accessor that the worker calls, which is a really handy one. It's just get CNF for a given node. So like if node 3 has access to clauses, index 7, 8, 9, then get CNF will be the CNF with only clauses that were indexed 7, 8, 9 in it. Get the CNF file name, that's only applicable if there are subfiles, if they're, it's directory. Compile CNF from message. So what happens is when the master gives the worker a message with various assignments, what happens is the worker needs to turn that into a CNF to pass directly to its CDCL. So the CDCL doesn't directly take in a message object per se. The message object specifies a node that has an associated CNF with it, and also various assignments that go along with it. So the assignments are appended to the CNF as unit clauses, right? So for instance, if you want to run that CNF with specifically assigned, variable 3 to be true, variable 5 to be false, etc., then what it needs to do is it needs to create a copy of the CNF for that node of the DAG, and then append -4 plus 5 as tiny unit clauses. Split CNF, and then pseudo split CNF is related to CNF splitting, and then it's got a whole bunch of private stuff here. So the CNF holder it's essentially a class that's probably most applicable to the worker, that just stores the CNF associated with each of the parts of the DAG. So there's multiple CNFs. The CNF holder holds multiple CNFs respectively, or the accessors to those. So that's the CNF holder. All right, let's move on. Okay. Now the worker has a CNF holder that holds CNF. It gets messages from the master, and what it needs to do is it needs to then pass those process CNFs that correspond to the messages from the master into CNF files to a CDCL process. Now there's 2 CDCL processes currently implemented in Dagster. That is inherent from the TinySat CDCL process, and also there's the MiniSat CDCL process. And those CDCL processes both inherit from a virtual class called satsolverinterface.cpp. So satsolverinterface.cpp h.cpp is basically like very vacuous virtual class. Load into message is solver unit contradiction, reset solver add conflict clause, solver append CNF, and destructor. So they're just basic, very, very basic. Method that the worker calls upon a generic CDCL process. Run with this message. Give me a result. Reset yourself. Add conflict clause, the negation of blah blah blah. Not particularly complicated. So basically, summary: I am the worker worker.cpp. I take and return message classes of work to and from master via MPI communications interface. I use a CNF holder to load and collate CNFs for work to do with, and I interact with an instantiation of a SatSolver interface class to process my work. So this is the worker. All right, so back to the diagram. So what we've done is we've talked about the relationship between master and the way it stores its logical work. We've talked about the worker and the communication objects that are used between the worker and the master at a high level, and we've talked about the worker itself and the objects that it uses to process its work. So now we're going to kind of move on a little bit to talking about other things. So the worker CDCL. So for instance, implementing the SatSolver interface is TinySat itself. So satsolver.cpp and worker and CNF manager.cpp are essentially the TinySat processes. So particularly CNF manager is straight out of vanilla TinySat. This file is part of TinySat, right? There's almost no modification here. CNF manager.h, CNF manager.cpp. This is vanilla CDCL stuff. It's directly copied and pasted from the originals, TinySat 0.22 CNF manager.cpp. So there's no thing there. The satsolver.h and satsolver.cpp is a bit more complicated. So because it's also taken in large part from the TinySat, but there is some modifications in it. So like this is like select literal, select literal via conflict. What does it mean to select literal via a conflict? Run method. So this is CDCL stuff. Verify solution. Am I a true solution to the problem? Now there's other stuff in here as well. So because the TinySat option has the option of communicating with the SLS and the strengthener, what it needs to do is it sort of needs to the CDCL TinySat process needs to be actively communicating with the SLS helpers to get suggestions from the SLS to communicate them, to communicate and access suggestions from the SLS helpers, and also to update its suggestions from the SLS, and to send the SLS prefix to tell the SLS workers where in the search hierarchy to kick off. And it also needs to interact with the strengthener so that, it will send periodically its clauses to the strengthener so the strengthener can strengthen them and then send the clauses back to the worker for reinsertion. So push to reducer is push to clause to the reducer. Add an arbitrary clause is the helper method to add to the CNF a strengthen clause. Get from reducer calls add arbitrary clause. Then there's the constructor method for the SAT solver, the destructor, and then there's a backtracking function. There's the backtracking search function that is inherent from TinySat. And then there's also a get solution from the SLS. So the SLS processes will periodically report a solution themselves. That what happens, and that's pushed into the TinySat buffer and then reported as a solution from TinySat to the worker, then consequently to master for master to store. And then there's sort of a phase logic here because the communication between the worker and the SLS process is partly async, so there needs to be a coherent phase variable so that the worker and the SLS processes know that they're working on the same work, even if they fall out of sync. The SAT solver has a get suggestions method, which then polls the buffers that it has from the SLSs. So a lot of this logic is not actually inherent so this is copied, a lot of this logic, not from TinySat itself per se. So earlier on in originals, original hybrid solver. So in original hybrid solver was the work that was done between Charles Gretton and Tate Kenningham, sometime 2019, I believe. So this here, this is a logic here. So that's where that comes from. So the idea being that this is the logic between the worker and the SLS helpers. So particularly the worker, every given depth in its search space sends a prefix to the SLSs to say work on that prefix, and the SLSs send back suggestions for the CDCL process to use as variable suggestions in its search process itself. And then, so that's essentially what's going on in the SAT solver class. This is probably perhaps less, is more organic class than I'd like. And then there's also the part appended by Marshall Clifton that was the communication with the strengthener module itself, right? So all of that goes in the satsolver.cpp, reset solver, and then print solution to file. So it's not actually complicated when you know what's going on, but it's perhaps less formatted nicely than what I would like per se, but it's not too hard. So this is 700 lines of pain, but 700 lines is not too bad. Right, and then that's the SAT solver. So satsolver.cpp, satsolver.h together with cnfmanager.cpp, cnfmanager.h is the TinySat process that is inherent of the SLS interface that the SAT solving interface that the worker instantiates. We are TinySat, satsolver.cpp, satsolver.h, cnfmanager.cpp, cnfmanager.h. And then there's we are Minisat, so this is the same thing but for Minisat. Now, Minisat's a little bit less complicated in a certain way. So inside of the subfolder Minisat solver, we have minisatsolver.cpp, minisatsolver, simplesolver.h, and a template. So a lot of this is it's largely copy from, so this is a small class that just wraps around what is essentially a vanilla copy of Minisat. That also, coincidentally, the strengthener uses as well. So the strengthener is based on Minisat. And also this here class, Minisat solver, that instantiates sat solver interface.cpp that the worker uses is just a thin wrapper around a Minisat process method. So simplesolver.cpp, this is, core Minisat, very vanilla copy of Minisat that says you solve with these variables and these values and these clauses. And it'll do its thing. Okay, so that's the Minisat solver subfolder. The actual folder minisat is just basically there's a whole bunch of utilities and like basic data structures and solver.cc is, this is like data structures that are copied directly from minisat repository without much to do. So we are the minisat procedure. And anyway, so the master communicates with its storage and communicates the worker work. The worker instantiates one of several possible CDCL processes, either a minisat CDCL process or a teenysat CDCL process, at which point the teenysat CDCL process sends work and interacts with SLS helpers and or strengthener. So of the SLS processes inside of the novelty. So inside of the novelty subdirectory, this here is novelty. So reversible integer map, we've come across that before. This is just a copy of the same class. The novelty main is just a very, this is the infinite loop while true of the novelty process. So this is, what it does is it essentially kicks off a receive to receive work from the workers that correspond to the assignments that master has given the workers. And then what it does is it kicks off from a various prefix, loads the CNF appropriate to that work, sets up the window that by which it communicates suggestions to the worker, loads in the prefix, starts up the main loop while true, does the SLS step while ever it can until it finds a solution, loads suggestions into the buffer. So this is the novelty has a suggestion buffer inside of the window that can be loaded multiple ways based upon novelty's various flips. Test for a message from the worker. So this is like if the worker's trying to tell it something. It's an async. If there's no message, then if it's found a solution, then you've got to send the solution to the master. Log novelty found solution. If prefix, then load prefix. Otherwise, free and delete. So this is the novelty. This is the novelty main loop. Is novelty main.cpp and novelty main.h. Now, novelty itself is a bit of a. So this is refactored code from the novelty original. So original's novelty plus. This is the original novelty process. It just takes a CNF and does the SLS process to try and solve a solution. So this is refactored into novelty.h, novelty.cc, like so, novelty.h. So there's a lot in here that we can't really get into because it's a bit... but this is actually well-written code because I rewrote this and it works. It really does. So basically, the SLS process is, sort of loads in CNF, loads in variable assignments, and then flips them to try and make the variables more satisfied. But there's sort of the way to do that most effectively, and then there's other tricks as well in there. So all of that. So this is inside of the novelty. Now you can refer, if you want, to the novelty paper that Charles wrote back in the day that actually detailed the novelty algorithm, or refer to the Dagster documentation for the details of the novelty process, because there's some finicky details in it. All right, so there's the novelty process. We are in subfolder novelty. What else we got?
Right, so there is the strengthener process. Okay, so in this we have the strengthener folder, and then inside of here we have what is the bulk of the strengthener. So the strengthener was coded by Marshall Clifton by a large margin, and it is inherent from a strengthening process code that was coded up some time ago. So before we do that, so inside the Dagster repository there is an originals folder, and there's the solver reducer, which is the source for this strengthener process, which was coded by the guys at Aalto University, circa 2013. And they coded up this kind of system that we've incorporated into Dagster, which is kind of functional. So it's built upon Minisat. We can turn back to the folder. So inside of the originals, there's the solver reducer code, gluco red, mini red, reducer, sol red version work X solver, and those files are more or less copied directly into Dagster, Xsolver, Reducer, Solred work. And they build upon the Minisat core, which is in the Minisat folder. So there's the core utilities and so forth. The strengthener is, so that the only thing particularly novel here is the MPI buffer that is coded via Marshall-Clifton, and the strengthener interface, which is the essentially the main loop for the strengthener process. So if we turn, it just consists of a surrogate main method, as we can see here, and the idea being that it's that while it receives, so the MPI receives a buffer length that it then consequently loads a message into, and then while it receives a buffer length of greater than 0, where 0 is kind of an exit trigger, what it does is it loads in the message and then runs strengthener. Loads in the message, loads the CNF. And then run strengthener basically boots up this Solred process, which is part of this system, and then kicks off the run reducing loop. So the idea being that the CDCL process that is the worker will periodically send clauses to this reducer process, and then this reducer will, in conjunction with the CNF that it's part of, seek to minimize or strengthen, because the smaller the learnt clause is, the more general and stronger it is, the learnt clauses that are given to it. Right, and it does this particularly, so there's the MPI buffer, MPI buffer.h, MPI buffer.cc, and essentially this is sort of like a rotating buffer of clause I/O that has been written here. And so the idea is that, it's just a periodic thing. Particularly, it kind of hooks up with satsolver.cpp, and then inside the satsolver, which is the TinySat, there is the where is it? Add arbitrary clause push to reducer method, and this is the interaction with the MPI buffer that is then consequently the interaction with the strengthener.
Right, what else we got? Oh yes, and the main method. So that's the only file that we haven't explained or gone over in some way. So standalone. All right, before I do that, standalone TinySat. So this is a superficial instantiation over, this is just a main method, instantiation over the TinySat process. So if you want to use Dagster's TinySat devoid of Dagster, you can use this. Conversely, inside of Novelty, there are 3 standalone versions of the Novelty code. So the Novelty.cc is the SLS code itself. And then if you go into any of these, there's a README and there's also like a main file. So this is if you want to run the Novelty process separate from Dagster, using the Dagster's refactored form of Novelty, this is a main method that you can call to directly work Novelty on a specific CNF, according to various rules. So there's 3 of them. And last but not least, there is the main method. So this is the main method. So there's just basically a bunch of initialization stuff. So let's go through this. So initialize Google logging, load the arguments from the command line, initialize MPI, load the DAG, load the CNF holder. If you're the master process and the command line arguments are relevant, then generate the decomposition. Otherwise, pretend like you did, because there's a thing. Then what you need to do is, if you're the master, if you're world rank 0, then you need to instantiate a version of the solutions interface, either that's table, master, or BDDs. Then there's also a process you need to seed the initial nodes of the DAG with an empty message. So this is the initial nodes that are stored as work to be done in the master process that kicks off all the subsequent work. Then you need to clear the DAG out file. So this is just open and close, if it doesn't already exist, with overwrite. And then basically what happens is, there's inside of Dagster, there's the mode parameter, -m. So this is like, am I TinySat, am I Minisat, am I running with strengtheners or not, am I running with SLS helpers or not? And this is mode 0, 1, 2, 3, 4. And so if you're mode 0, then enter that mode execute function. And the mode execute function will then subsequently kick off all the workers into all of their worker loops. Anyway, once the mode X is finished executing, then what you need to do is you need to log the solutions and dump them to a file. spit out the sats, and then exit. So now the mode 0 execute, mode 1 execute, mode 2 execute, mode 3 execute, mode 4 execute is basically separate logic. So all workers, when they MPI run, will kick off the main method, and the only difference between them will be their the world rank. So master is always absolute rank 0 in the MPI world, and then all of the subsequent ranks are workers of some sort, right? So they might be the TinySat CDCL workers, they might be SLS workers, or they might be strengtheners for those workers. And so the idea is, depending on what mode you're initializing, there's a different allocation scheme for what workers to be executing what main loops to correspond to what kinds of workers they are. So let's take the simplest of them, is mode 0 execute, which is up the top. So mode 0 execute is just basically saying there's one master and then everybody else is worker. Right, so what it does is it sets up a communicator, master communicator, to communicate between the master and the workers. If world size is less than 2, so basically, if there's only one master and no workers, then you can't do. So world size must be greater than 1 MPI abort. And then it instantiates the communicator for which master is going to be communicating with his workers via MPI. It sets up the comms interface using that communicator, and then it passes it to the master and the worker processes. If world rank equals 0, then you're a master process, go into master loop. Otherwise, you're a worker, go into the worker loop. That's mode 0. So that's the simplest of the modes, and then subsequent different modes are a little bit more complicated than this. So mode 1, so this is master and then workers, and then also SLS helpers for those workers. Right, so what it needs to do is it's a bit more complicated. So basically there's a communicator between the master and the workers, and then there's the communicator between the workers and its helpers. So there's subcommunicator, strengthener. Oh, and this has strengthener as well. So if your world rank 0, so if the world size is not congenial to this mode, then you've got to exit. If world rank is 0, then you are the master process. Join the communicators that you are subscribed to as master. Generate the comms interface that you're going to be using as master. Create a master class. Dump yourself into the worker loop. Otherwise, you're a worker of some kind. And then it sort of does this sort of indexing logic to try and group the remaining workers and or strengtheners into approximately equally sized groups. So there's actually a logic here. So number of processes per hybrid group, and then there's like a modulo here, and then there's like a renormalization here. If you've got like an odd number of workers left over, it will try to pull them into another group. In any case, MPI com split to the appropriate group that you're part of. If you're the index in the group 0, then you are a CDCL worker. Otherwise, you're a novelty. So if index in group equals 0, you're the worker, you're CDCL. If index in the group is not 0, then you are one of several novelties associated with that group, and you will go into the novelty main. Anyway, so like mode 2 execute is the most complicated, where you've got workers and strengtheners and SLSs, and each of them need to be like, if your world rank 0, you're master, otherwise you're a worker. And then there's extra complicated index modulo arithmetic to figure out, like if you're a worker in group X or if you're a strengthener in group Y, then you need to subscribe to the appropriate communicator. And then depending on what modulo you are in the group, you're either the CDCL, you're a strengthener, or you're the worker of some kind, and you're a novelty. And then equally so for mode 3, mode 4. Mode 4 is the easy one because it's minisat rather than TinySat, same thing. Anyway, and that's the main method. That's the main method class. By the way, if there's a better way of doing this logic, and I'm sure there is, rather than just having a whole bunch of functions, it feels like a bit of an awkward way to code it. But anyway, that's the master method. That's the main method. Alrighty. Thank you for coming with me to the end of this tutorial. I hope that has somewhat clarified what the parts of the code are and aren't, and what they do and how they're related to each other. We'll see potentially upcoming tutorial number 5. Otherwise, have a lovely day.